I want you to think about um, the ultimate paradox of modern life.
Oh, it's a big one.
It really is, because we have all seen firsthand how microscopic particle, I mean, something far too small to even see, can just completely shut down global borders.
Yeah, empty out airports, close schools.
Exactly. It can fundamentally change how billions of people live. It is a force of nature that can literally bring human civilization to a total standstill.
Right.
And yet, if you take that exact same entity and you just leave it alone on a doorknob or, kitchen table, it is completely helpless.
Utterly helpless.
It is as inert and powerless as a grain of sand. I mean, it can't move, it can't feed itself, it can't grow. So how on earth does something so utterly helpless hold so much power over us?
It is a staggering contradiction when you put it like that.
Right.
We are just so used to associating viruses with panic and illness that we rarely stop to look at what they actually are.
We just see the threat.
Exactly. To truly understand this paradox, we have to kind of strip away the fear and look closely at the invisible mechanics of nature.
Because it's not malicious.
No, not at all. That inert particle on the doorknob isn't plotting against us. It's just a very specific, very strange piece of biological architecture.
And that is exactly our mission for today's deep dive.
Yeah.
We are going to explore the fascinating, almost alien mechanics of viruses.
It really is like alien technology in a way.
Yeah. We are going to break down exactly what they are, how they manage to hijack our bodies, and why they might just be one of the most misunderstood forces in nature.
And we're doing this from the ground up.
Yes, assuming zero prior science background from you, the listener. So if biology wasn't your favorite subject in school, don't worry, we have got you covered.
No textbooks required.
Nope. So to understand how something so helpless can be so powerful, we first need to look at its physical architecture. Okay, let's unpack this.
Let's do it.
Because the physical description of a virus from our sources is, well, it's incredibly minimal. It is basically just two main parts.
Just two.
Yeah, you have the genetic instructions, which is the code, and a protective protein coat, which acts kind of like a seed shell.
And it is hyper-minimalist. I mean, when people think of microscopic threats, they usually picture bacteria.
Sure, yeah.
But bacteria are fully functioning single-celled organisms. Viruses are tiny, even by the standards of the microscopic world.
Like how tiny are we talking?
They are far smaller than bacteria. So small, in fact, that you can't even see most of them with an ordinary light microscope.
Wow.
Yeah, there is almost nothing to them. They have absolutely zero machinery for feeding, growing, or reproducing.
So I was trying to think of a good everyday analogy for this. And the best way I can picture it is like a piece of malicious code sitting on a USB drive.
Oh, that's a great way to look at it.
Right. Because if that USB drive is just sitting on my desk, it is completely harmless. It's just plastic and metal. It's just a message in a capsule.
Exactly.
It can't run the code, it can't spread, it can't do anything until it is physically plugged into a computer that actually has a processor and a power source.
And the living cell is the computer in that scenario.
Right.
If you contrast that viral capsule with a living cell, like the ones that make up your body, or even just a single bacterial cell, the living cell is this bustling, complex factory.
It's doing stuff all the time.
Constantly. It takes in nutrients, it generates its own energy, it builds proteins, and it has the internal equipment to copy itself.
The virus has none of that.
None of it. It is
Yeah.
completely missing the hardware, which sets up a very stark reality, To do anything at all, the virus is forced to find a host.
Now, some viruses also have one extra little feature on the outside of that capsule. They have a greasy outer envelope wrapped around that protein shell.
Yes, the lipid envelope.
And for you listening, this is exactly why everyone is always telling you to wash your hands with plain soap and water.
It's so important.
You don't need fancy antibacterial chemicals. Plain soap is chemically designed to dissolve grease.
Right, like when you wash a frying pan.
Exactly. So when you wash your hands, the soap molecules literally pry apart that greasy envelope, completely destroying the virus's capsule.
It just falls apart.
It's such a simple mechanical way to disarm this terrifying thing.
It really highlights how physically vulnerable they are outside of a host.
Yeah.
Without that greasy envelope, the virus just degrades into the environment. It is a highly fragile system.
So it's basically a ticking clock for the virus once it's on the doorknob.
Exactly. Since the virus is just an inert blueprint with no machinery of its own, when it does manage to survive on that doorknob and eventually get inside us, it has to find a way to steal someone else's machinery.
So if it has no engine, no arms, and no way to move on its own, how does it actually get through the front door of a human cell that is actively trying to keep it out.
That is the big question.
This brings us to the actual infection process, the biological break-in. So the virus is just drifting around in the fluid of your body, totally inert, until it bumps into one of our cells.
Just entirely by chance.
Right. And this moment of contact works like a key fitting into a lock. The virus latches onto a very specific receptor on the surface of the cell.
It has to be an exact match.
But wait, so if it operates strictly like a lock and key, why don't we catch diseases from our pets? Like if my dog sneezes on me, shouldn't that viral key work on my cells too?
Well, what's fascinating here is the absolute specificity of that lock and key mechanism.
Okay.
The receptors on the surface of your cells are structurally different from the receptors on the surface of your dog's cells.
Oh, I see.
They are shaped entirely differently. So a virus that has spent thousands of years evolving a quote-unquote key to fit perfectly into a human respiratory cell will likely just bounce harmlessly off a dog's respiratory cell.
Because the key just doesn't fit the lock.
Exactly. It has no way to gain entry. The physical shapes simply do not match.
But when they do match,
When the lock and key do match, the cell is tricked into opening the door and the biological break-in occurs.
and once it gets past the door, it injects its genetic code inside our cell. And here's where it goes from being a helpless grain of sand to a total master manipulator.
It really does.
It forces our own bustling cellular factory to stop its normal, healthy day job and instead start manufacturing hundreds or thousands of copies of the virus.
It weaponizes your own biology against you.
That is so sinister.
It is. Because the cell is full of molecular machines that just blindly follow instructions.
They don't know any better.
Right. They don't know the difference between their own genetic blueprints and the viral blueprints that just got injected.
So they just get to work.
Yeah. The cellular machinery starts reading the viral code. It starts building copies of the viral genetic material, and it manufactures new viral protein codes.
Wow.
It just does this over and over until those parts assemble into a massive swarm of new virus particles inside the cell.
And because the cell is putting all of its energy into building viruses instead of, maintaining itself, it's essentially working itself to death.
For a second.
Eventually, those thousands of new copies just burst out, completely destroying the host cell in the process, and they go off to invade the neighboring cells.
And that cascade is what causes the real damage.
Right, and is that cycle of cellular destruction, combined with our own immune system rushing in and launching a massive inflammatory response to fight it, that actually makes you feel sick?
Yes, people often get that confused.
Yeah, the fever, the aches, the fatigue, that isn't the virus doing that to you directly. That is your own body going to war, turning up the heat to try and burn the virus out.
And the virus itself isn't actively malicious. It's just relentlessly efficient at copying its instructions, using your energy and your materials.
But knowing that a virus is completely inert until it crashes into a compatible cell, well, it forces scientists into a very tricky corner.
It really does.
It forces the scientific community to wrestle with a genuinely difficult philosophical question,
Oh, the big one.
which is a virus actually alive? And I have to admit, looking at the arguments on both sides from our sources, it gets incredibly dizzying.
It's one of the longest-running debates in biology.
We are constantly battling an entity that, depending on who you ask, isn't even fully alive.
Because it raises one of the most fundamental questions in science: what exactly defines life?
Right?
A virus sits right on the fence. If you look at the alive side of the argument, a virus has genes. It carries the fundamental code of life.
Okay, makes sense.
And crucially, it evolves. It mutates and adapts to its surroundings over time.
Which is exactly why we need a new flu vaccine every single year.
Exactly.
The flu virus mutates, its key changes shape slightly, and our immune system has to learn how to recognize the new version. That ability to adapt and change shape definitely sounds like something a living creature does.
Evolution and carrying genetic code are major hallmarks of living things. But
Yeah.
then you flip to the not alive side of the argument.
Right.
As we discussed, it cannot reproduce on its own. It sits doing absolutely nothing indefinitely outside a host. It cannot self-repair.
Wow.
And perhaps most importantly, it has no metabolism.
Okay, wait. When you say it has no metabolism, do you just mean it doesn't eat? Because I hear metabolism and I immediately think of, like, burning calories at the gym. What does that actually mean for a virus in a biological sense?
That's a great question. In a strict biological sense, metabolism is the ability of an organism to take in energy like food or sunlight and process it chemically to maintain itself, grow, and function.
So it's basically the engine.
Yes, it is the engine of life. A cell takes in nutrients and chemically burns them to keep its factory running.
Okay.
A virus does none of that. It doesn't eat, it doesn't breathe, it doesn't process energy in any way whatsoever. It has no engine.
It really is just the USB drive sitting on the desk.
It is. Biologists basically place viruses in a strange in-between category. They are not quite alive, and they are not quite dead.
It's just hovering there.
Exactly. They exist poised on the very boundary of life. It demonstrates perfectly how nature refuses to fit neatly into the rigid binary boxes humans try to sort it into.
Nature doesn't care about our definitions.
Not at all.
But because we naturally view viruses entirely through the lens of human disease and pandemics, we end up missing a massive part of their story. We miss the fact that they have fundamentally shaped all life on Earth.
That might be the biggest misconception we can clear up today.
Yeah.
It is a mistake to think of viruses purely as villains. By sheer numbers, viruses are the most abundant biological entities on the planet.
The scale of this is just hard to wrap your head around. Our sources noted that there are more viruses on Earth than there are stars in the observable universe.
It's mind-boggling.
They vastly outnumber all other forms of life combined. And the crazy part is, most of them have absolutely nothing to do with humans at all.
The vast majority infect bacteria, particularly in the oceans.
Okay.
And in doing so, they act as a crucial regulatory system. They keep microbial populations in check.
So they're kind of managing the ecosystem.
Exactly. If a certain type of ocean bacteria starts reproducing too quickly, viruses will infect them, thin the population, and release nutrients back into the water. They help shape and balance entire global ecosystems. But their influence goes even deeper than just population control.
How so?
Because viruses shuttle genetic material into cells, sometimes pieces of that code get left behind. They act as genetic couriers across the history of life.
Okay, here's where it gets really interesting. Because when viruses accidentally leave scraps of their code behind in a host's DNA, sometimes that code actually gets adopted by the
It
host.
becomes part of them.
Yeah, there is an example of this in our source material that is just a massive paradigm shift. A scrap of ancient viral code got woven into the DNA of mammals millions of years ago.
It's incredible to think about.
And that specific borrowed viral gene is actually essential to how the placenta forms.
It is truly a mind-bending twist. The protein that allows a mammalian mother to form a placenta and therefore nourish a growing embryo inside her body originated from an ancient virus.
That is just wild.
It was a viral protein originally used to fuse the virus with a host cell, allowing the break-in we talked about.
Right, the door breaking open.
Evolution eventually repurposed that exact same fusion mechanic to fuse placental cells together, creating the barrier that protects the growing baby.
Which means live birth, the very foundation of how humans and all mammals reproduce, relies on an ancient virus.
Yes!
The very agents of disease that we fear so much are actually responsible for mammals existing at all.
If we connect this to the bigger picture, over the long sweep of evolution, viruses haven't just been destroyers.
Right.
They have acted as random upgrade generators.
Upgrade generators, I love that.
By constantly moving genetic material around, shuffling the deck, they occasionally hand highly useful new code to their hosts. They have been agents of change, actively shaping the code of life itself.
That is just incredible. But of course, while ancient viruses may have given us the placenta, modern viruses still cause tremendous suffering when they hijack our cells today.
Sadly, yes.
Which leads us to the final piece of the puzzle, the medical arsenal. Given that viruses are woven into our evolutionary history and that they physically hide directly inside our own cells, how do we medically fight the harmful ones without accidentally hurting ourselves?
That is the ultimate challenge in modern medicine, and it explains a very common and very dangerous confusion.
Yes.
We have to make this absolutely clear. Antibiotics do not work against viruses.
So what does this all mean for you listening? It means when you have a terrible viral head cold or the flu, you should not go to your doctor and demand an antibiotic prescription.
Please don't.
But why? Why do antibiotics work so miraculously on a bacterial infection like strep throat, but do literally zero against a virus?
Because antibiotics are highly specific weapons designed to attack the machinery of bacteria.
Okay, the machinery.
For example, many antibiotics work by destroying the bacterial cell wall or gumming up the bacteria's internal protein factory so it can't function. But remember our earlier discussion about the physical architecture. A virus doesn't have a cell wall. It doesn't have internal
With
factories.
just the USB drive.
Exactly. It has no machinery of its own to poison.
You can't blow up a factory that doesn't exist.
You really can't. Taking antibiotics for a viral cold does nothing to stop the virus.
Right.
Worse, it exposes the helpful bacteria naturally living in your body to the antibiotic. Over time, those beneficial bacteria survive the exposure, mutate, and become antibiotic resistant.
So you're actually making things worse.
Yes, overusing antibiotics for viral illnesses is actively breeding superbugs.
Okay, so if antibiotics are entirely useless against viruses, what are our actual solutions?
Well, we have two main defenses.
Vaccines and antivirals.
Right.
Now, a vaccine, as we know, is basically showing your immune system a harmless preview of the virus, maybe just handing it the protein code, so your body can train its defenses and recognize the lock and key mechanism in advance.
It's a training exercise for your body.
But I want to focus on antivirals. Why is it so much harder to create an antiviral drug than it is to create a new antibiotic?
It comes back to the biological break-in. Because the virus is using your cellular machinery to reproduce, poisoning the virus usually means poisoning the host.
Oh, because it's inside our own factories.
Exactly. It is incredibly delicate precision work. An antiviral drug has to somehow surgically jam specific steps of the hijacking process, like blocking the virus from attaching to the receptor or jamming the copying of the genetic code.
But without hurting the cell, it's inside.
Without wrecking the human cell it's hiding inside, you are trying to stop a process that is intimately intertwined with your own biology.
It's like trying to stop a bank robbery when the robbers are perfectly disguised as the bank tellers, using the bank's own computers and writing with the bank's own pens.
That is a perfect analogy.
You have to somehow stop the fraudulent transactions without shutting down the entire bank or hurting the real tellers.
And that level of precision makes antivirals incredibly difficult to engineer.
Which makes sense.
And that is why vaccines remain our best defense. Training the body's security guards to recognize the robbers before they even get inside the bank is far easier and far safer than trying to root them out once they've taken over the factory floor.
Absolutely. So to recap this incredible journey for you today, a virus is not an evil mastermind. It is, at its core, simply a message in a capsule.
Just a piece of code.
Left alone, it is a completely helpless piece of code, devoid of an engine, devoid of metabolism, sitting squarely on the boundary of what we consider life.
Right on the edge.
Yet once it finds a host factory to hijack, it becomes formidable. And while they are agents of disease, they are also some of the most influential forces in shaping global ecosystems,
They really are.
acting as genetic couriers that have profoundly altered the evolutionary story of life on Earth.
And that dual nature leaves us with a fascinating final thought to ponder. Yeah, if a scrap of ancient viral code was repurposed to create the mammalian placenta, making live birth possible, what other fundamental human traits might actually just be ancient viral code waiting to be discovered in our DNA?
That is wild to think about.
When you look at the deep history of evolution, it forces us to ask, are we, in some small, unacknowledged way, more virus than human?
Wow. Next time you look at a perfectly inert doorknob, just think about the invisible, almost living history resting right on the surface, waiting for a factory. Stay endlessly curious, everyone. We will catch you on the next deep dive.